Hello, this is Tony Hiller from RealClimateScience.com. H.L. Mencken said, "For every complex problem, there is an answer that is clear, simple, and wrong." With the record cold coming to the United States, I posted a poll on Twitter. What do insulators do? Only one answer is correct, and the two possibilities were stop heat from escaping or increase the temperature. Almost everybody responded with stop heat from escaping. That answer sounds very simple, but if the insulation in my walls was keeping the heat from escaping, why do I have to keep the heater on? Reality is that the insulation in the walls doesn't stop any heat from escaping. If we turn the heat off for a couple days, temperature inside the house will be the same as the temperature outside the house. So let's take a look at what insulation actually does. This is the heat conduction equation. Q is heat flow. It's proportional to the temperature difference between inside the house and outside the house. Heat flow is also proportional to the thermal conductivity of the walls and inversely proportional to the thickness of the wall. A thicker wall will reduce the rate of heat flow. And an insulator reduces the thermal conductivity, which also is going to reduce the heat flow. So having a thick layer of insulation in the walls will tend to reduce the flow of heat out of the house. But the heat wants to get out of the house, so what happens is the temperature difference increases between the inside of the house and the outside of the house. By increasing the temperature difference between the inside of the house and the outside of the house, the heat flow speeds up. You're happy because the inside of the house is warmer, and the heat is happy because it's escaping like it wants to do. And this is where I point out that this simple diagram, which I copied off of sciencefacts.com, is incorrect. There's an error in the equation which is causing the heat to flow in the wrong direction. Your homework is to figure out what that error is. We see a similar principle to heat flow in any kind of flow equation. If you put your thumb over the end of a garden hose, it doesn't stop the water from flowing, but rather it increases the pressure right next to your thumb, which makes the water flow faster. Insulation in the walls increases the temperature difference, and putting your thumb over the end of a garden hose increases the pressure difference. But in both cases, you're not stopping the flow. Another example is how electric resistance heaters work. The heating element adds resistance to the wire, which makes it more difficult for the electricity to flow. This produces a large difference in the voltage from one side of the heating element to the other, which is analogous to putting your thumb over the end of the hose and increasing the pressure. The increase in resistance causes the electrons to speed up in order to compensate, and as a result, heat gets generated inside the heating element. The resistance element doesn't stop the flow of energy, but rather it converts some of it from electricity into heat. The most fundamental principle of energy is that it always wants to flow from areas of high energy to areas of low energy. This is in fact how Earth maintains its balance, and it's a principle which climate alarmists don't seem to understand. They have all these crazy theories about tipping points and Earth spinning out of control, when in fact the behavior of the climate and the behavior of science in general is the exact opposite. After summer comes winter, and after winter comes summer. After a drought, it rains, and after it rains, we get a drought. Nature's always trying to move towards low energy, balance, and equilibrium. Many common scientific principles are simple, but they're not necessarily obvious. Toto has been teaching people about science for almost 16 years, and I've been doing it for a lot longer than that. You can visit us on the web at realclimatescience.com.